Actually, the original order was supposed to be the fine-tuning for life and the fine-tuning for scientific discovery. Somehow it got mixed up. So I'm going to do the fine-tuning for life because the fine-tuning for scientific discovery sort of builds off that. So that will be my next talk. So if you were coming in specifically for the fine-tuning for scientific discovery, that will be in the second talk in the next hour. So I'm going to begin on the fine-tuning argument for life. A few of the slides I noticed didn't quite come out right when they get translated into this format, but it's not severe, so it shouldn't be much of a problem. Okay, so the fine-tuning design argument, that's what I'm going to look at in this talk. And it's an argument from physics and cosmology for the divine creation of the cosmos. And here's the big issue. It's commonly assumed that modern science undercuts belief in God. I will argue just the opposite in this talk, that actually the discoveries in the last 50 years or so supports divine creation. And we will look at here on the fine-tuning of the basic structure of the universe. This should be differentiated from the older design argument from the that William Paley used of the intricate structure of plants and animals. Many people believe that that was undercut by the theory of biological evolution. This is not undercut by that theory. So, in fact, the cosmos has to be fine-tuned in order for evolution to even occur at all. So in the last 50 years, scientists have discovered that the universe is analogous to a biosphere. Its basic structure must be precisely set for life to exist. And so I give an example here of a biosphere out, a tourist attraction now setting out in Arizona, in which everything had to be adjusted just right for human life to exist in there. It happened to not be adjusted just right, so it had to be evacuated in 2 years. A key assumption here is that the relevant kind of life is what I call embodied conscious agents. These are agents that are conscious, have bodies, and can interact with each other in what they consider moral considerations, and that such agents require stable, reproducible complexity. So there's 3 types of fine-tuning that can be distinguished: the fine-tuning of the laws of nature, the fine-tuning of the constants of physics, or the fundamental parameters of physics, and the fine-tuning of the initial distribution of mass energy at the time of the Big Bang. So what is the fine-tuning of laws? First of all, what is a law? That's just a basic principle in physics, like the law of gravity, that all masses must attract each other, or one of the laws of electricity, that like charges repel each other. To say that the laws are fine-tuned means that the universe must have precisely the right set of laws in order for highly complex life to exist. And I will consider 5 of about 14 examples. Example 1 is a universal attractive force of gravity. So we do a thought experiment here. What would the universe be like if gravity did not exist? Well, first of all, there wouldn't be any planets, because if gravity did not exist, all the matter in the universe would just be kind of uniformly distributed in one clump together. There also wouldn't be any stars. Stars are needed in order to provide the energy needed for life. That's due to the second law of thermodynamics. If there weren't any energy sources like stars, then the second law of thermodynamics says things go from order to disorder, so life would very quickly go from an orderly state to a disorderly state. That's why we can't exist that long without food, for instance. And so you need stars. Stars also give you the early stars in the universe produced the elements needed for life, like carbon, for instance, are produced in stars. And there's a whole interesting story about that, actually a very fascinating story about how the stars, early stars, function as giant factories for the higher level elements, carbon, all the way up to the radioactive elements, which are also needed for a life-permitting planet. So that's one example. If the universe didn't have gravity, there wouldn't be any life. The other example, second example I'm going to use, is that of the electromagnetic force. And that refers to the combination of the electric and magnetic forces. And one of the most important discoveries in the history of humanity was that of James Clerk Maxwell, because he united the two forces in the 1800s. His equations for how the two forces related together allowed for radio, television, explain light, which is an electromagnetic wave, allowed for electric motors, transformers. So our technological civilization really began with major beginning with James Clerk Maxwell's uniting of these two forces, which allowed all that to happen. So the existence of the electromagnetic force, a combination of those two forces. So one aspect of that force is the electric force. As shown in this diagram, if there weren't any electric force, there wouldn't be anything to hold the electrons around the nucleus so they could orbit the nucleus. And if there'd be no chemical bonding and therefore no life. A further consequence of the electromagnetic force is the way the electromagnet relates to the magnetic force allows, or actually causes, in the right circumstances, the transmission of an electromagnetic wave. That's a vibration of, alternatively, to electric field that gives rise to a variation in the magnetic field, and so on and so forth, giving rise to light. That is needed in order for light or energy to come from the star to a planet. If you didn't have a means of getting the energy from one to the other, you couldn't have life, because life couldn't exist on like a star like the sun, too hot. So you need the electromagnetic force. It also plays it plays that role, and that shows a kind of ingenious design to nature, that singular things like the electromagnetic force often play multiple roles. So it's very elegantly put together. It also, as we'll look at later when we talk about the fine-tuning for discovery, the electromagnetic force also gives rise to radio waves, all the kind of communication we have today. So is actually its form is allows for our technology and our ability to discover the universe. So we've looked at now the gravity, the electromagnetic force. In the next several slides, I'm going to dwell into more into the building blocks of life. So we already talked about an atom with the electrons going around the nucleus. But here's a question that immediately comes up when Rutherford, in around 1900, hypothesized the existence of a nucleus consisting of protons and neutrons. So the protons are positively charged, so we know that like charges repel each other. So if you just had that model of the nucleus, you would have the protons would repel each other and the nucleus would fall apart. So you need an additional ingredient. And it has to be a force of a special kind that holds it together. It's kind of a glue. And it's the strong nuclear force. This was in my old days. That's me, my old days before I went into philosophy. If you know American politics, it was before I ran for the governor of California, which was Arnold Schwarzenegger, who won. So the strong nuclear force, it holds the protons together. It has to be of the right form. It can't be like gravity, which is a long-range force, and also electric force is relatively long-range. Like gravity can reach from the sun to the Earth, holding the Earth in orbit. If the nuclear force were that way, it would breach other atoms, other nuclei, and pull them all together into one huge clump of matter that would turn into a black hole. So it has to be the right kind of force, which is called a short-range force, which requires a very particular structure of the force, and it has to be stronger than the electromagnetic force. So there had to be a strong nuclear force that was hypothesized, and then later they developed a theory of how that force came about. So that's another ingredient, the strong nuclear force. Now you might think you're done. You've got your nucleus with the strong, protons and neutrons, and then you've got electrons going around held together by the electric force, and you might think you've got a workable atom. You would be wrong. There's another problem that immediately arises, and electrons or any charge, when it's being accelerated, which for physicists means it's not going in a straight, a thing that's not accelerated is going in a straight line with the same velocity. It's not doing that, it's being accelerated. So an electron going in a circle is accelerated. And charges that are accelerated emit electromagnetic radiation. So that's how your cell phone works. There's a little antenna in there, and the charges go back and forth over 1 billion times a second. And by doing that, they emit a radio wave with a frequency of about over 1 billion times a second. And that's how you can communicate with it. So that would be a problem here, is because if the atom had electrons going around the nucleus, then they would be accelerating, and so they should lose energy and immediately, as this diagram shows, crash into the nucleus. That doesn't happen. So realizing that, Niels Bohr, who is the founder of the Bohr model of the atom, had to hypothesize a special rule, what's called the principle of quantization, that the electrons could only occupy fixed orbitals. So there has to be a new rule in place. But this rule later was found to come out of a much deeper theory called quantum mechanics. But if you didn't have this rule, you wouldn't have any viable atoms. And so you might think you're done. You've got the nucleus and orbitals, so you've got the building block, the atom, for life. Once again, you would be wrong, because another problem arises. And the other problem is this, is that things like to go to their, if they can, to their lowest energy state. So what would happen is, even if you had only had fixed orbitals, the electrons could be in, they would all fall to the lowest energy orbital here around the nucleus, and you wouldn't have any complex life, because complex chemical bonding needs the outer shell electrons. That's what's responsible for it. So you need a principle to keep that from happening. And the proposed principle was called the Pauli exclusion principle, which you might have learned about in school, that effectively implies that only at most 2 electrons can occupy any orbital. So that means once there's 2 electrons in this orbital, like in a carbon atom has 6 protons and 6 electrons, so it has 2 electrons here, can't have any more, so 2 there in the second orbital, 4 electrons, and then 2 more in the outer orbital, and you get carbon. So that's another principle you need. Interestingly, that principle is extremely important. It serves another role. It keeps matter from all collapsing in on itself, and that was proved in the 1960s. It was proved that without this principle, all the charges in matter would rearrange themselves, and within like 1 billionth of a second, all matter would collapse in on itself. So there wouldn't be any solid surfaces, there wouldn't be liquid. So the world would basically cease to exist. And interestingly, the Pauli exclusion principle, there's no deeper physical explanation in terms of little particles with kind of material powers that could be responsible for this. It's just a rule. It's a mathematical rule that says nature behaved this way. In fact, that's most of modern physics. It just consists of a set of mathematical rules without any deeper physical explanation for those rules. So a theist might just think God upholds those rules directly. So here I've only looked at like several of about 14 examples, and the ones I've looked at where you have to have the right laws are gravity, electromagnetism, strong nuclear force, principle of quantization, Pauli exclusion principle. This is just to give you an idea of the kind of right sort of rules you have to have. You also have to have things like rules that protons, without a rule called baryon conservation rule, that protons and neutrons should just decay away, and so you wouldn't even have those. So you need a bunch of additional rules. Somewhere around 14 of them you need to have life. So special rules. Now, what's been most discussed in the literature is the fine-tuning of the constants of physics. And what are these? These are numbers that occur in the fundamental equations of physics. I prefer to actually call them fundamental parameters, but the word constant is stuck because they might not be the same throughout space and time. We don't know for sure. So they are numbers that occur in the fundamental equations of physics, and they must be precisely adjusted to an extraordinary degree for life to occur. So here's an example, the the gravitational constant. So there's what's called Newton's law of gravity, and I give it here. It's the force between any two masses, let's say you, your body, and the Earth. That's the force of gravity between you, is equal to this number called G. That's a constant. That's just a number. It has a particular value with units. Times your mass times the mass of the Earth divided by the distance between you and the center of gravity of the Earth squared. That would give you what's called the weight, which is how much on a scale your body would push down on a scale. So you can see the fundamental role this plays. If you were to make this twice as large, your weight on Earth, how much you're pushing down on the surface of the Earth, if you made G twice as large, that would be twice the force. If you made it 1/2 as large, that would give you 1/2 the amount of force. Now, I'm not a medical doctor, but I'm still going to give you a piece of medical advice. If you want to change your weight, which is the force on a scale on Earth, don't try changing G. Tried and true weight is changing M1, your mass. So that's the gravitational constant. Now that requires an extreme fine-tuning for there to be life. And so we want to ask, how fine-tuned is the constant? So we have to look at the range of force strengths in nature. And there's a dimensionless way of measuring this. And you can think of it as the force, it's approximately the force between two protons in a nucleus. The two protons in the nucleus will have a really teeny force of gravity between them. They will have an electromagnetic force between them. That's the repulsion of the two positively charged protons to each other. And there would be the strong nuclear force I talked about before between them. Now, the strong nuclear force is about 10 to the 40th power. That's 1 followed by 40 zeros, as strong as the is gravitational force. That is 10,000 billion times the strength of gravity. So that gives you the range, a huge range of force strengths. And to appreciate this range, we can imagine a ruler stretched across the visible universe. And that is 15 billion light years approximately across. And a light year is how far light travels in a year. It travels 300 million meters in a year, which would be 300,000 kilometers, per second. 300 million meters per second, or 300,000 kilometers per second. And there's about 86,000 seconds in a year, or a day, and 365 days in a year. So you could see how an incredible distance it travels in a year, and multiply that by 15 billion. You get how far the visible universe we can see in the visible universe. And the strength of gravity, if you had that ruler stretched across that visible universe, the strength of gravity would be here would be the strength of the strong nuclear force, and the strength of gravity would be in the first trillionth of an inch. So you can see the huge range of force strengths. So now you can do thought experiments. So imagine increasing the force of gravity by 1 part. It should be 10 to the 31th there of the range of force strengths. That is a billion-fold increase in force strength, so not 10 to the 34, 10 to the 31, which is still a huge amount. That's 1 part in 1 followed by 31 zeros. In that case, even single-celled organisms on Earth would be crushed. And only planets less than around 100 feet in diameter could sustain life with our brain size. Such planets, however, could not contain an ecosystem. What happened to my PowerPoint? Well, let me go to is there a problem with my PowerPoint?
Professor, is there any problem switching the slides?
There shouldn't be any problem, but I don't know. Is it just it? I could reload the slide as the best I could do. Want me to try reloading it?
Well, actually, we have the first page of your slides. Probably there are 3 dots on the top of the screen. If you click on that, you can manage the slideshow.
Okay, well, I'll go to let's see where I was.
Yeah.
Okay, I was here. Okay.
Yes.
Okay, so here. Okay, so picking up again, I think we'll probably be okay because I went through the slideshow before. And it seemed to work. Okay, that's around 100 feet in diameter. So if gravity is too strong, all life forms in the strong gravity world would be crushed, and there couldn't be any ecosystem. The planet would have to be too small. Worse yet, and I'm going to get back to the full screen here. Worse yet is that you can't even, billionfold is a huge increase, not very much compared to that range. That would only bring us up to the first thousandth of an inch. But if you do other calculations, you can show that even a small increase starts requiring that you increase the surface force on a planet. Very quickly, you have to increase the surface force a lot in order to retain an atmosphere. So, like if you a 400-fold increase in gravity, retaining an atmosphere, meaning that the gravity has to be strong enough to keep molecules from the atmosphere from going out in outer space. They slowly do it now anyhow, but they would do it a lot faster. So if you increase the G 400-fold, your gravity would have to be 10 times as large, the surface force. And then, like if you increased another 9-fold, they'd be 30 times as larger. You can see very soon it wouldn't be very good for life forms like us and body-conscious agents. Thus, in order for life to occur, the strength of gravity must fall within an exceedingly narrow range of values compared to the total range of force strengths. It must fall into an even narrower range in order for the surface force in any habitable planet to be optimal for embodied conscious agents, and I should say optimal also for them doing science. So it seems to not only be fine-tuned for life, but even more so in a kind of optimality range. So here's an analogy. If you thought of it, this is an old style radio that I grew up with, where you had to tune in the radio station. We call them in the West Coast of the United States. There was a K in front of it. So you can imagine that radio station K Life. You'd have to tune that dial within, if it was stretched across the universe, within 1,000th of an inch if you wanted a universe for a life. So extreme fine tuning. So it's very difficult to imagine that just happening by chance is the upshot of it. The most discussed case of fine-tuning in the physics literature is that of the cosmological constant. And that's a term in Einstein's theory of gravity that influences the expansion rate of space. And we'll be running into that more in my next talk. It can be positive or negative. Unless it's within an extremely narrow range around zero, the universe will either collapse before galaxies and stars can form, or it will expand too rapidly for them to form. It's also, when it's positive, it's called the dark energy density. You might have heard of that, the universe being composed of around 70% dark energy. So it has to be within a very small range, calculated about 1 part in 10 to now the 120th power. That's 1 followed by 120 zeros. So it has to be much, much less than a trillionth of an inch, given, let's say, a ruler stretched across the universe. It has to be extremely fine-tuned. So many of the constants of physics must fall into an exceedingly narrow range of values for life to exist. If they had slightly different values, no complex material systems would arise. This is widely recognized. For example, the late Stephen Hawking recognized that they must be finely adjusted to make development of life possible. Dennis Sciama, formerly director of Cambridge University Observatories, said if you change a little bit the laws of nature, or you change a little bit the constants of nature, it is very likely that intelligent life would not have been able to develop. So that's on the constants. I've looked at the laws, basic rules by which the universe operates. The constants are fundamental parameters of physics. And then now I'm going to look at the final one, the initial distribution of mass energy in the universe. So that has to be extremely finely tuned in order for life to exist. So as if you just looked, if you're standing at the beginning of the universe, it would just seem like just a big ball, according to the Big Bang Theory, which I completely accept, a just big ball of energy without any structure, but it has to actually have a lot of very precise structure in order to get life, or a precise order, if you want to put it in those terms. And so it's kind of analogous to a zygote, the cell, for example, that turns into a human being. It looks like a blob of protoplasm if you just looked at it, the surface, but if you looked at fine details, you would see it has to have a lot of structure to produce a human body. So how precise must this initial distribution of fine mass energy be for life to exist? You can ask Roger Penrose, one of Britain's leading theoretical physicists and cosmologists. And so he gives here, just using the idea of a creator as a kind of way of illustrating this. I don't think he actually believes in God. He says, in order to produce a universe resembling the one in which we live, the creator would have had to aim for an absurdly teeny volume of phase space of possible universes. Phase space is just the space of all possibilities, like the phase space of when you flip a coin is heads or tails. A phase space of 2 coins, base possibilities of which they could land, is heads, heads, tails, tails, heads, tails, and tails, heads. So he says it would have to be 1 part in 10 to the 10 to the 123rd power. Notice it's not just 10 to the 123rd. It's 10 raised to 10 to the 123rd power. That is just unimaginably, this is unimaginably large number, and this is an unimaginably small number. So let's try to bring that into human comprehension. So to get an idea, imagine you have a photocopying machine. That's, say, God's photocopying machine. It does it really fast, and all the paper you ever wanted. And then you put a 1 in, you produce all these papers all covered with zeros, and you fill the entire universe with those papers. And then you put a 1 in front of all those papers, all those zeros. The resulting number would be vastly smaller than the number, somehow it's cut this off, the number we just saw of 10 to the 123rd power. So that gives you an idea of how large that number is, 10 to raised to 10 to the 123rd power. So the initial distribution of mass energy must fall within an unimaginably narrow range of values for complex life to occur. The calculation I just said that Roger Penrose does is a fairly straightforward calculation, so is widely accepted. So a recap of the fine-tuning: we have the fine-tuning of the laws of physics for life, the fine-tuning of the constants of physics, or what I'd call better called fundamental parameters of physics, and the fine-tuning of the initial conditions of the universe. And also the constants seem to be precisely adjusted so that living conditions would be optimal, and be optimal to develop technology and discover the universe. And I'll be talking about this in my next talk. So here is a student of mine, did this on one of my exams years ago when I first started exploring the issues. I had circular dials. Dials are perfectly set, life can exist. Dials imperfectly set, no life. That's the idea. That's for the parameters of physics. So we have what's called in philosophy a cumulative case argument for fine-tuning. Many different facts all point to the same direction. So even if one of the claims is not as well supported, if we find a problem with one of the claims, there's so many of them that we have a really strong case for fine-tuning. It's like having DNA evidence, fingerprint evidence, witness testimony, confessions, so on and so forth in a murder trial that all point to the person being the murderer. That would be a very strong case, stronger than any one of those pieces of evidence. So then the question comes up, how are we to explain the fine-tuning for life? So to many people, the fine-tuning immediately suggests some sort of divine creation. This is true for theists and non-theists. So this is William Blake's Ancient of Days, God Creating the Universe. Of course, this is a very anthropomorphic image of God that no theist, no knowledgeable theist would accept, but it's only for illustrative purposes. So non-theist theoretical physicist and popular science writer Paul Davies notes when looking at this and other aspects of the universe, the impression of design is overwhelming. So notice he's not just saying this because he believes in God. He notes this even though he's not a theist. And Sir Fred Hoyle, a very well-known non-theist astrophysicist and cosmologist, when he first discovered one of the claims, one of the cases of fine-tuning, he says a common sense interpretation of the facts suggests that a super intellect is monkeying with physics and that there are no blind forces in nature. So what alternatives do non-theists offer to divine creation? Here are the main ones. First alternative, it's just a lucky accident. The fact that a life-permitting universe exists is just a coincidental fact that neither has nor requires an explanation. Our existence is just an extraordinarily lucky accident. Let's look at that. Many people find this as completely implausible, as claiming that the face of Abraham Lincoln, a famous U.S. president, was just the result of an ink spill. So if ink spill would be extraordinarily improbable for it to come out in the face of Abraham Lincoln. That's one criteria for not saying it just happened by chance. And the other is not only being very improbable, but there's something special, recognizably special about it, as you'd have with the face of Abraham Lincoln. So that's one alternative. Physicists and cosmologists who think about this, almost all of them reject that alternative. It's more popular among philosophers. But the second alternative is what's called the multiverse hypothesis. So if we spilled ink enough, maybe we would get the face of Abraham Lincoln. So that's the idea of the multiverse hypothesis, according to which there are an enormous number of universes with different initial conditions, values for the constants of physics, and even the laws of nature. So just by chance, we're going to exist. Some beings, somewhere, there's going to be a universe that's just right for life. So in this idea, humans are winners of a cosmic lottery. So it just happens, enough lottery tickets are produced over and over again, and eventually the winning number is going to come up. That's the idea. And we'll see this also explanation needs what's called the observer selection effect. That will be relevant for the next talk. So here's some advocates of the multiverse hypothesis. Cosmologist Max Tegmark, who I've met and talked to about it. Met actually a couple times at various conferences. Sir Martin Rees, I've also talked to him about it. He was some former astronomer royal of Great Britain. I don't know if he's still alive. And cosmologist Stephen Hawking of Cambridge University. And here's several books on it, fairly recent. Many Worlds in One, The Cosmic Landscape is another book on it. And this is a book with essays both for and against, or essays discussing it. And I have one in here that argues that certain kinds of multiverses are compatible with theism, but points out that non-theistic multiverses run into significant fine-tuning problems themselves. And then here's another one, a recent book by Stephen Hawking, The Grand Design. And I don't think much of this book. It has really, it dismisses philosophy and then goes on to make a lot of really serious errors in thinking of their philosophy. It says that cosmologists, we don't need philosophy more because we have cosmology, and philosophers haven't kept up, as though cosmology could address questions in ethics. And then it goes on to say the universe creates itself out of nothing via gravity, and that's impossible. Not even God could create God's self out of nothing. And then they say that we used to think things were as they appeared to be, but modern science shows us otherwise. And if you just think about history for a moment, you know that most people in most cultures did not think that. They believed in a whole nother invisible dimension. And Copernicus, who developed the idea that the Earth goes around the sun, and it rotates, is not what it appears to be. It appears the sun goes around the Earth and the Earth is still. So it just seemed like it was they didn't really think about what they had said in those regard. And to me, it was an example of science arrogance, that they think because they could do cosmology or physics, then they can speak on everything. And I experienced that when I was a graduate student in physics, that some of the physics professors would look down upon every other discipline except mathematics, which they considered more rigorous. So anyhow, that's a side comment, but I think an important one when you talk about these issues, that a lot of the people that write these things haven't really thought about the philosophical side and just dismissed the philosophy. So not all of them. So the multiverse hypothesis comes in two major versions. One, that all possible realities exist. So dream up a story you like, it exists and it's consistent and it exists somewhere. This is not widely advocated. The other version is what I call the universe generator version. And this is the idea there's some physical process that generates the universes. And this is my cartoon image of it in the conveyor belt here with universes being produced. And every time it produces a universe, it randomly adjusts some of the fundamental parameters and initial conditions and even the laws of nature. So the most talked about or viable one of this scenario is inflationary cosmology combined with what's known as superstring theory, in which there's a kind of pre-space that produces all these bubble universes, and the pre-space is expanding at an enormous rate. So very quickly it can produce an enormous number of bubble universes, and the superstring theory allows the constants and fundamental parameters to be randomly shuffled. And possible theistic responses to that: takes more faith to believe in many universe generator than God. That's how some theists would respond. Where did the universe generator come from? That would be back to what's called the cosmological argument. And what I'm going to focus on is the universe generator itself would need to be well constructed to produce a single life-sustaining universe. And next talk will focus on this one. It doesn't account for optimality of the universe for science and technology. And then there's you can ask me about that in the question and answer session, the Boltzmann brain problem. So as an analogy for the problem of the universe needs design, I used to have what's called a bread machine, that you put flour and gluten and various other things in there, and it produces a loaf of bread. But if you didn't correctly operate it, or it was it wouldn't, or it was malfunctioning, without the right ingredients, it wouldn't produce a decent loaf of bread. So it has to be well built even to produce one decent loaf of bread. How much more if you're producing universes? And in the article I had mentioned that I have in that book, I discussed that, the inflationary superstring scenario, and show that explicitly. So it doesn't really maybe takes away a little bit of the fine-tuning, but it largely just transfers it up one level to the existence of the universe generator itself. So the claim is universe generator itself does not significantly undercut fine-tuning, and theism is compatible with the mini-universe generator. So 3 responses to fine-tuning evidence: theism, belief in God, multiverse hypothesis, brute fact. Many people can't believe this one. This one tends to push the design up one level, so you seem to be left with theism. And you can, here on the slide, you can go to a further debate I have on this. But I want to say one other thing, that often people say that theism itself runs into this who designed God objection. And so that'll take me just a couple minutes, and I want to say something in response to that, because that's the most common objection you get. It's really promoted by Richard Dawkins, the leading popular atheist, and that's really his only objection to the design argument. And so I'm going to have to go here to quite a few slides ahead, and just real briefly, and this will be all I'll have to say, and then we can go into question and answer session.